So my name is Satish. I'm a resident solutions architect with Databricks. Been with Databricks for a while now, for 2 years in Databricks terms. That's quite a long time because almost everybody over there is like less than a year old. So apart from a few. Uh, in terms of my background, I come from a financial services background. A lot of data related work at financial data companies. Primarily at NYSE, where you sell one little thing about financial data is, stock exchanges make more money selling data than actually trading. So, uh, so basically, I used to run one of the data platforms over there. We would basically sell, curate a lot of this financial service data coming from a bunch of different exchanges, and then provide it to firms that use that data to make decisions about what to buy, what not to buy, and that sort of stuff. One cool thing today is I got my Moderna vaccine. So, I do have some superpowers today. Wanted to try them out, but I was told not to. I apparently have to wait for the second dose as well. So, anyway,
I'll be waiting for the full demonstration of your powers.
Yeah. All right. So let's get started with the streaming. So the agenda today, I'm going to talk about what is streaming, why would you want to use it? For a lot of people who come to big data, you come from a typical, ETL type background where you're used to your dimension models, your fact tables and whatnot, and you're able to, build these, translate some of that background knowledge, when you go to a big data platform very easily. But streaming seems completely, out of the left field where, it is fundamentally a different concept. It seems real time. And ETL workloads are not particularly real time. You build it, you deploy it. Even if you're not a big data world, you still are doing your aggregate views, your materialized views, and then you're reporting off of your dashboards from there. But streaming kind of fundamentally changes that. So hopefully I'll try and narrow down in terms of what is fundamentally different about streaming. How do you reason about streaming? What streams are, and how do you think about them as part of your overall data pipeline architecture. Part two will basically get into some of the reference architectures in terms of how do you do streaming at scale, especially when you're trying to deploy large pipelines, and many pipelines that need to be up and running almost, with first thing, you have requirements around latency, you have requirements around, uptime, and, we cannot really afford to lose data at all. So, and then we can, and towards the end, we'll talk a little bit about Delta Lake, how those kinds of technologies help with streaming. And then, as we go on, and then, if time permits, then we can get into more of the hardware level details of what kind of machines, how do you think about clusters and all of the good stuff. But at a high level, I do have a quick demo to show you in terms of code to, how do you build a stream, starting from say something like Kafka, and then build something out pretty fast. But the overall focus of the talk really is about more of the architecture and the design concepts rather than, here's a short tutorial on how to build a stream. Okay. In terms of questions, I'd appreciate if you can interrupt me in the middle and then ask the question, then hold on to it until the end. It just helps with this structure in the discussion better.
Yeah, so don't be bashful. Feel free to unmute.
Yeah.
Turn on your camera on or not, and ask your questions.
I heard that one of the giveaways today was going to be dinner with Satish. If that's not true, I think I might leave. Can you guys let me know?
Possibly. All right. What is structured streaming and why use it? Just a little bit about history about where structured streaming comes from. People, I'm going to assume that you're reasonably familiar with what Spark is. That's my baseline. If not, Spark is, in a very crude terms, is a big data engine that kind of came about into the open source space around 2012, 2013, where it got a lot of traction. Essentially, companies that were doing a lot of Hadoop type work, we're just put off by the scale and the amount of maintenance that you need to kind of run your Hadoop clusters. And Spark, with its completely in-memory data processing model, just changed the game in terms of how do you do that kind of big data workloads. One of the first implementations of streaming within Spark was part of the 1.x version of Spark, which was called as D streams or discretized streams. streaming was completely rewritten as part of the 2.0 or 2.1 or 2.2 implementation of Spark, where it became structured streaming. So right now, almost always anybody who uses Spark streaming is typically using structured streaming and not dstreams anymore. The dstreams API is still there. It's fairly low level. It's difficult to implement, but if you have sub-millisecond latencies and some kind of super high what do you call SLAs that you need to meet, then discretized streams is still the option to go. But often up to, if your SLAs don't exceed like 100 milliseconds or something, structured streaming is pretty good in terms of being able to process it. And I'll talk about in terms of why that difference exists when we get into the talk. Okay, that's a little background about like what streaming is and what is structured streaming and why does Spark do it. Among other players in this particular space who do streaming, one of the most exciting projects is something called as Apache Flink. Apache Flink is one of those other projects that does streaming, that then they do claim that they do real-time streaming. I'll talk about what Spark does, which is also called as mini batch streaming. So we'll get into that, but they do talk about what they call as real-time streaming. All right, so what is streaming? So when people talk about streaming, we think in terms of like primarily a processing engine that is getting a lot of incoming streams of data, right? Whenever I say streaming, that's what first comes into your mind, that there is some kind of queue or a topic where stuff is coming in, and then there is an engine that's letting you process these things. Essentially, if you come from something like a Apache MQ or Cupid or any of these other back in the day, what they call enterprise service buses background, like it's kind of analogous to it, where data shows up on a stream and then you pick it up and then process it. In a big data scenario, it's a little bit different. One thing you need to understand is, when you compare a stream and a batch processing engines, there is how you get the data, which is, is it coming continuously or is it coming in as a batch? And then there is the concept of what is a bounded versus an unbounded data set. When we talk about a bounded data set, we say the amount of data that you're going to process is limited. In a batch processing engine, the full set of data. It's a CSV file that's sitting over somewhere, or it's a Parquet file that's on a bunch of different folders. But in a bounded data set, when you come to a stream processing engine, it still is going to come row by row. It's not as if you're going to get the full data set in a single shot. It's still going to be coming row by row. The flip side to it is what called the unbounded data set. Right? In the batch processing world, there is no analog to what an unbounded data set is. You can only consume what is already there. So by definition, your batch process is, what has been written into that data set. If you need to add on to it, it's going to be another completely ETL pipeline that you will need to run, or the pipeline run it repeatedly, a few times a day to catch up. Whereas in the case of streaming, when we talk about an unbounded data set, that works because you're getting data in real time and you're able to listen and consume this data frequently as the data shows up. Right. So if you think about streaming as an in-memory data structure, and then in the case of a bounded data set, that even though the data might have come via streaming, it's still adding on to the memory structure over a period of time. In an unbounded data set, it's the same story. It still adds on to the same in-memory data structure over a period of time. The only issue comes is what we call in terms of when unbounded is is it stateless or stateful? Like how long are you going to hold on to this in-memory structure, before you decide the kind of processing that you're supposed to do with it. Like so one way to think about, another way to think about streaming really is, and if you're coming from an ETL or a database-centric view, you think of it as there's an unbounded input table that is kind of maintained within the database, and then the stream just is adding on to it at the bottom, one after the other. So every message that you get on any of the streaming apps, when I say streaming, I'm really talking about something like a Kafka or an Event Hubs in the case of Azure, or in Kinesis in AWS type scenarios, right? So what we're talking about really is the message that's coming on one of your streams really is simply adding on to the unbounded input table. So the new data in your stream basically gets added as a number of rows to the input table, and this input table still is going to act as any other table in the Spark ecosystem. It's a table that's there. You would query a SQL table with SQL. If you query it one time, you get a bunch of 1,000 rows. You query it after a few milliseconds. Maybe the data has come in between, and then now you get a few extra 1,000 rows. But the structure of what the underlying database or underlying inbuilt memory data structure is still going to be the same. It's basically an unbounded input table that Spark maintains for you, and then that just gets every stream that's read basically gets sorted onto this unbounded input table, and that's the right way to think about in the case of Spark. What is a stream? A stream or a streaming query literally is creating this data structure in memory for you, and everything else just simply follows on top of it. You should be able to interact with this table as you would with any Spark table. You should be able to read it, aggregate it, and do all sorts of operations on top of it, just like you would do with a standard SQL type table that you have in Spark. Right? So structured streaming basically brings this unified view where the semantics of how you think about a data frame, which is the primary data structure in Spark, is pretty much the same between whether the data frame is powered by either an underlying static file data, or if it's powered by a Kafka stream that's continuously spewing messages at it. Right. As far as the user is concerned, you think of a data frame object as a table with a bunch of rows, and then you would interact with it almost exactly similarly. Right. So in terms of just thinking about what the processing model looks like, there is the input table, which is what we talked about as the data frame object that's holding on to the data. There is a user query, and then there is a result table, right? So if you think about in the batch case scenario, this pretty much is your static view of the world, whereas the input table reflects your underlying CSV or Parquet or any particular data structure that you might have. A user query simply aggregates or does some kind of manipulation of data on top of this particular table, and then you get another table back, right? In the incremental execution on streaming data, it translates almost very similar to it, and that's where the unified view of the data structures between batch and streaming comes in play. The input table is exactly the same thing. The incremental query will always give you a result table, and then you get a result back. But the only difference over there is this concept of time that you see at the top, right? As the time moves along, the input table gets populated with more and more data as you start reading from the underlying stream. So the table keeps changing as you go on, and the query results also keep changing over a period of time. Now that depends on, of course, your query. If you're only looking at for results from time to T1 and T2 and so on, if you're doing some kind of a query that looks at results in the beginning of time, then of course your query results are going to be getting added. So the method of thinking about how do you process data that's coming in a stream is no different fundamentally between a batch ETL table versus a streaming ETL table. The structure is exactly the same, and we'll talk about the red box, the output mode, and why the input mode a little bit more in the next couple of slides. But essentially, the conceptual model is generally the same, right? And that's what I'm trying to get across in terms of that's the biggest advantage of the structure streaming concept is that once you understand how data frame works, how these Python APIs or Scala APIs work in terms of querying tables and whatnot, that knowledge should translate to a streaming structure fairly straightforward without any issues. Right. All right. So why use streaming instead of batch? Streaming handles a superset of the use case requirements. Can deal with incomplete unbounded data, which is what we're talking about in terms of when we say incomplete data, what we really mean is data that is not complete at the point of time that you're looking at. It might be complete at a point in the future, but at a given snapshot of time, somebody might deem it as incomplete. Now, there are different ways of dealing with the incomplete data, and Spark streaming has multiple different modes. There is something called as standard stateful streams, and there's a concept of sessionizations or flat map groups with state. I'll talk about them in a little bit and the use cases where those things apply. But streaming can help you with handle these incomplete data that is fairly often in real-time scenarios. Provides much lower latency. But then, because this is streaming, because you don't know when the data arrives, because it's unbounded and the data continuously arriving, won't that be very expensive, requiring an always-on cluster? And the short answer is actually yes, it is. It is expensive. You can make it cheaper and affordable and, tune it correctly to kind of limit the amount of resources that you have to put in. And there are different modes of doing this. But apples to apples, streaming is an expensive operation compared to a batch type of ETL. Again, like differences vary in terms of the amount of data and the cluster size and all of that. But all else being equal, streaming is definitely an expensive operation. Okay. All right. What is a typical processing engine requirements for processing streams, right? Because the alternative option, if you don't have a streaming engine, is to run the batch 10 times a day or 20 times a day or whatever it is to be able to get there, right? One thing is correctness. You need something called as an exactly once delivery guarantees. Now, anybody coming from a Kafka background, or even event hubs for that matter, would understand this very clearly, which is Kafka or any of these large scale pipelining message broker type solutions guarantee what is called as at least once guarantee delivery. What that means is, if there is some change in the underlying, let's say you have a topic that's partitioned across 12 partitions, and you have a broker that has 5 nodes or 6 nodes or so. So each partition, each node has, let's say, 2 of the partitions, and irrespective of how how it works, anytime there is, let's say, a node goes down, whatever happens, there's a whole repartition access that Kafka runs. Whenever a repartition runs, Kafka will probably end up redelivering a bunch of different messages back to you again, right? So what Kafka guarantee really guarantees is at least once guarantee, at least once delivery. What that means is that it'll guarantee that no matter what happens to the cluster underlying cluster, you'll at least get the message at least once. But there is a big risk that you will get the message multiple times, right? So, but that is not the case for the streaming engine. The streaming engine has to find a way to basically process the message once and only once. Just because Kafka is delivering it twice doesn't mean that, you like, if you're a simple database application, you might have to deal with duplicate messages, but the streaming engine out of the box should be able to provide a guarantee that says, I'm gonna process this particular message only once and only once. You're not gonna let idiosyncrasies of Kafka or event hubs affect your processing. Cannot cut corners using approximation. Now, this is typically the Lambda architecture, where you have an ETL pipeline that is at the top, or a batch pipeline at the top and a streaming pipeline at the bottom, where you approximate your data, or you approximate how frequently the data arrives to be able to aggregate and provide this. But in the real-time streaming scenario, that's not really an option. You really have to process all the messages, everything, all the data that has showed up at the point of time, right? And more importantly, you need to be able to deal with out-of-order events. Now, this is a much bigger problem than any of the other issues, primarily because out-of-the-order events are super difficult to handle in stream, simply because when you have an unbounded stream, when you don't know when the end of the stream is going to come, there's no good way to distinguish, when, what is the particular order of the event. Serial IDs don't cut it. Serial numbers don't cut it. Time is a bit of a malleable thing over there. So, we'll have to deal with all of these things over a period of time as you build out these architectures. So next, I'm going to talk about, to basically deal with these things. Now, how does Spark and structure streaming in Spark basically solve for all of these issues, and what are the constructs that you need to be aware of in terms of dealing with these particular issues when you build a real-time streaming application? Any questions so far before I go further? Good. Thank you. Reasoning about time. The first thing that we talk about in streaming is time. Time is a moving target over there. So what is an event time? So the event time is the time at which the event actually occurred, and that typically shows up in the data as a payload object, or as an attribute of the payload, right? Often, this is the more interesting thing that or at least business critical thing that you're worried about, but that's not what the streaming engine actually sees. Processing time actually is when the data is actually processed. Often, there is always a delay between when the event happens, when the event actually shows up on your Kafka pipe, right? Your event happens, let's say 10 seconds ago, and there is a time lag between when it shows up on the Kafka bus. But the processing engine has no clue about what it's supposed to do with it. It is going to think of it as, hey, here's a brand new arrived event, right? Now you'll need some constructs within the application to be able to reason that event time is a more critical thing. Let's say if you're gonna wait for a bunch of events to show up before you do processing time is not gonna cut it. It has to be the event time. So your stream processing engine should be able to figure out a way to read the event time and then hold on to the event time or track the event time to be able to kind of, to tell you that, hey, I think I've gotten all the messages that are probably belonging to this particular stream of data, right? So irrespective of whether you're processing, in the case of stateless stuff, stateless streaming, where where the stream doesn't have a state, every message is independent. It might not actually belong to a particular group of things. These are, let's say, you have tweets that are coming, like not a Twitter thread or anything, but if you just have random tweets coming at you, those are good. Like, there's no concept of a state. You can process them, as they arrive. You don't have to wait for stuff. But in a case of an unbounded data where you're waiting for things to show up and where it doesn't make logical sense to process anything until everything shows up, this concept of event time and processing time kind of becomes super important. And it becomes important, especially in the case of data streams that spew large volumes of data, because you're holding these in memory, and memory is finite, and there's only so much that you can hold on to it before your cluster crashes and burns, right? So here's a simple way of showing when batch processing time per definition is much later. When you with the time you process the event is like much later when the event has occurred. But in the case of streaming, we assume data to be complete, or we settle for incompleteness. In the case of streaming, processing time often is close, seconds, minutes, milliseconds often. But the challenging is, when the processing time greatly exceeds the event time, can you do anything useful with it? Can you conclude anything useful with it? But so the goal is the streaming engine should be able to kind of handle these constructs where when the data shows up might not be a useful thing to actually worry about, but actually when the event actually happened. So what results are calculated? We saw this, and where in the event time of those results calculated. So just in terms of the data flow model, right? So we talked about when you start building a stream and you have a concept of when the time is and how you're going to think about event times and processing times. The next question that we ask is like, okay, what is the data structure that you're going to use? How do you calculate the results on top of it? When in the event time are these results calculated? When the processing times are materialized? And how do you store these results? Because not every results are going to be insert only. There'll always be append. There's always be updates. There's always be overrides. So essentially, these are the 4 things that you kind of think about in terms of when you set up a stream. That is, what are you going to calculate? When are these things calculated? And when are they materialized? And what does this particular materialized view actually look like? So these are the four things that we'll actually get into a little bit more deeper in terms of the actual code itself, like how these things are done. Okay, so what results are calculated? These are determined by transformations that you run. You select, filter, group by, etc. as per the data frame API. So once you set up a data frame that's filling up as data comes in, you calculate some results, and then that is basically using the data frame API. This is the unified view where it doesn't matter whether you batch or whether the data frame is a batch data frame or a streaming data frame, except for few operations that are not support in structured streaming. For instance, simple things like limit or distinct. These things don't have a meaning in a streaming scenario, simply because your limit doesn't really mean that has no way of telling Spark what it needs to do in terms of limit. Like, is it limit of 1,000, 100? And distinct again doesn't mean anything because this is getting modified in real time. There are ways of doing distinct on a streaming data frame, but it's not exactly same as Spark.read stream, get a data frame back, and then if you call .distinct on it, you will get unsupported exception simply because it's not going to be able to do a distinct on it on a stream that's continuously getting updated in real time. Right? But most other operations should be able to be done. And if there are things that are directly not supported in structured streaming, there are ways to doing it where you take a batch streaming data frame that's coming. You take a streaming data frame that's coming in. And then convert that to a static batch data frame thing by doing something called as a for each batch. And then on top of it, then it's a regular data frame, and you can basically run whatever operation that you need to run. Okay, where in the event times are these results calculated, right? So this is where we introduce the concept of what is called windows. Basically, if you think of it this way, as a window is essentially a time window, right? Or it could be key-based windows, and we'll talk about what those things are. A window is a way to think about is your state of the data frame between one snapshot of time for that matter and another snapshot of time, right? How frequently does the window change? If you have a fixed window, then you're saying, what, hey, snapshot my stream every 5 minutes, and that's my window of processing. I'll take every 5 minutes of data that has arrived. I'm going to process it, and then I go back and process my next 5 minutes of window. In a fixed window, the window doesn't slide. It is like from 12:10 to 12:15 is one window, 12:15 to 12:20 is the other window, and so on. A sliding window is one where you define a window as of length, let's say 5 minutes, but then the window slides, which means 12:0 to 12:05 is one window, 12:05 to 12:10 is another window, and 12:10 to 12:15 is a third window. But you aggregate the events across these windows. So the window just simply keeps sliding by 5 seconds or 5 minutes or 3 minutes. So how frequently the window slides is different between the length of the window itself. Right? You could have a fixed length window, but that slides every 10 minutes or every 5 minutes, depending on what your business operation is. Now, if you expect that events that have happened have a delay of up to 10 minutes, then you may want to have the window that is from 12:0 to 12:05 actually slide slower, like basically wait until like 10 minutes and then slide, which is when, and when we say slide, we mean that is when it is being submitted for your operations, which is your select operations, your group by operations, and all of that stuff, right? You basically are sliding the window at a different length than what the window itself is, right? And then there is this concept of sessions. Now, this is a little bit of a different concept where there is no concept of a time at all over here, because these events that happen that determine what a window is, what a unit of operation is not particularly time driven. A simplest example that we often see is something like you watching TV, right? And Disney streaming, for instance, when somebody starts a stream and then when somebody ends a stream, doesn't have a fixed length, right? You're clicking off, opening Netflix and then starting to watch a movie is start of an event. And if Netflix wants to see how many times you've paused, how many times you've forwarded a portion, how many times people skip credits, those are all events that Netflix is actually collecting in real time and publishing them to their internal message bus, right? But how do you know when a user started and a user stopped? There's no good way to do it until you click your TV stop button or you go exit the app and go to another one. Netflix has no clue how long this window is actually going to be. So if I'm holding on to data for a user like you and waiting for you to fill up the window, I could be waiting for a long period of time before the window of full events fills up and I actually make sense of the whole thing, right? These are called as sessionizations, where it doesn't make sense to talk in terms of windows, but actually in terms of sessions. So what is the key that you need to be able to see when to say a list of events that have arrived are now ready for processing? And then until they are ready processing, you still have to hold them in memory, right? Okay, so these are different types of windows or different types of aggregates that you kind of hold on to when you're talking about streaming. Like how frequently does the data arrive? Is there a lateness to the data? How long are you going to hold on to it? Is there actually a time component at all, or is there a more event type or event key based type thing that determines what your unit of aggregation really is, right? So, yeah. So when in the processing time are these results materialized? So what we mean by that really is, okay, we've said here's a window that for which we're going to collect these events that as they arrive, but when do you process them, right? So this is where triggers, watermarks, and output modes kind of come into play, right? How frequently do you trigger, which is how frequently do you go and collect data? Watermarks is, how long are you going to wait for late arriving data? And then eventually, once you're ready to calculate, once you calculate your result out of the incoming data, where you're going to put it, how you're going to put it, and that sort of stuff, right? Triggers. A trigger basically is some kind of a time-driven event that tells when do you start a new mini batch. So let me go back a step back, right? So I said Spark implements streaming as a mini batch. What we mean by that is internally by default, Spark basically runs every 100 milliseconds. It basically goes and looks at your Kafka bus or any kind of your streaming source to see has any new data arrived. That's what we call a mini batch. Basically, if you have 1,000 messages that have piled up on your Kafka broker in the last, let's say 100 milliseconds or so, Spark basically is going to drain the full Kafka broker at that point of time and append them to the data frame in that particular mini batch, right? Now you can tune this mini batch to be longer. You could have it as every 5 minutes because that's the frequency at which the window arrives. But the lowest that you can go is 100 milliseconds, I think. And that's the minimum amount of time that Spark's going to take, right? And that's what we call a trigger. Now you could have an unspecified trigger, in which case the mini batch polling happens every time every time the previous mini batch was finished completion. That is, I've picked up the previous one, I processed it, now I'm ready to go process the next one. And we'll talk about the state in a little bit. Or you can have a fixed interval, which is start a new mini batch after the last one completed and X time has passed. This is a fairly common use case. Common use case where you have an always on stream, but you're not expecting a lot of data to come in, where maybe you deployed like 50 streams on a single cluster, not very traffic intensive streams. So not everybody's going to run their mini batch at the same time. So it's okay to basically stagger them over a period of time. Right? That's one way you manage cost, by putting in a bunch of streams on top of on a single cluster. Okay, but triggers pretty much define when you process some data. There is a concept called as a run once trigger, which means that you don't really need to have an always on cluster, but you can have like hey, my input data still comes as a stream because for whatever reason, the existing structure, people are publishing stuff onto Kafka, but I don't need this data, in real time. I can maybe pick up the data like, twice a day or thrice a day or something like that, or maybe once a day. What you could do really is basically have this thing called as a run once trigger, where when the stream comes up, when the cluster comes up, the query runs once, drains the entire Kafka topic, processes the whole thing, and then simply shuts down. So that's a run once trigger. And you do this 3 times a day or whatever the frequency that you need to. And then that's how things get processed, where there is no query hanging on to process data as it goes on. It's a fairly common pattern that we see in the field where, where the latency requirements or the processing requirements are not as stringent. Yeah, that's the one-time trigger.
Is that exactly the same basically as a batch processing at that point?
When you say batch processing, this is the case where you're actually reading off of the stream object, right? So it's still a stream. It's just that you don't want to do this mini batch polling type thing. You just want to basically drain the whole thing in one shot and be done with it.
So with that one time, you can shut the cluster down and not pay for it to run 24/7.
Exactly.
But it can fire up like once a day or on that schedule.
Yeah.
Okay.
Okay. When in processing time are these results materialized, right? So this is the concept of when are we going to process this? We said the trigger is when in the processing time are we going to pick up the results, right? But now once you come into this concept of state, when are you going to actually materialize them, right? Now this is the case where we're writing a simple query that we're writing. We're saying words are group by. So we words is your data frame that is actually a real time, is actually a streaming data frame that you're reading. And you basically are saying, my stream length is 5 minutes or my window length is 5 minutes, but I'm going to move the window every 10 minutes. Okay, so which means that at a certain period of time, I actually have 2 windows active and live happening, and I'm going to move the window every 10 minutes or so. So sorry, my 10-minute window is sliding every 5 minutes. I apologize. So in this case, what happens as the events start arriving, let's say this event called as these are just words that are arriving on a Kafka on a topic. So and you're just doing a count of these things. So you have a window which is from 12 to 12:10, where it's simply putting the number of cats that have arrived, because that's the count, that operation that we're running on top of it, right? So the window, if you look at, because it slides every 5 minutes, the window that got started at 12, which is going to span from 12 to 12:10, slid at 5 minutes interval, so that with a count as cat is 1 and dog is 3, right? And then a new event showed up at 12:07. In this particular case, because the event arrival time is 12:07, but the window length for us is 10 minutes, this is going to get added to the previous window. So So if you look at there's a thin line over there. So this got added to the previous window, which was the 12 to 12:10 window. But because this slides every 5 minutes, this got added again to the other window, which is the one that started at 12:05 to 12:15. So if you think about it, there's two windows that are now active. Now became active around 12:05. The earlier window that started at 12 o'clock, which is going to span until 12:10. A new window, because you said the starting time is 5 minutes. A new window that got started at 12:05. So that is this window as well. So now you have two windows that are rolling together that are going to be moving every 5 minutes, and you'll eventually will get collected. We'll keep on collecting all the events that arrive over a period of time. Right. Now, you don't ideally want to hold on to these windows. So if in this particular case, what ends up happening is the moment you do the dot write stream and trigger, the window that was complete. So if you had a 10-minute window and it's lit for 5 minutes, and then at 12:10, the window that was started over here would be ready to kind of process. So that window would have been processed, and once that is processed, that is removed off of memory. So essentially, you'd be carrying forward only those two windows going forward. Okay. Now, okay. So this is the case where we say, how do we handle late data? So this is the concept of what we call as watermarks, right? So what we in a very simple scenario, a watermark literally is take the most recent event time that you've seen and discard any lay data after a configurable stateless threshold. What it means is, instead of blindly relying on your system time to say, when to discard something that is not arrived, right? You basically say, what? Let me look at the event time of the event object itself. Right? I'll look at the most latest event time that I've seen. And if you have a threshold for that, because the data might be arriving late, but if the event time I've seen is, let's say, the most recent time that I've seen is, let's say, 12:14, right? I know that I've gotten at least most of the events until that time, right? And if you give me a threshold that says, until 10 minutes before that, have a threshold as 10 minutes prior to whatever is the most latest event time that you've seen, I'm okay collecting events that have arrived at 12:04 as well, right? So that's my watermark. And when does the watermark move? The watermark moves whenever I get a brand new event with a new event time. So if my watermark right now is 12:14, I keep on collecting events, until they've arrived even 10 minutes late. So an event that might have occurred at, 12:05, 12:06, even though my current time is different, I'm going to keep on adding that to my window until I see a new event arrive with a new event time, which is, let's say, 12:20. Now I know that the brand new event that I've seen is 12:20, and my watermark says it's 10 minutes prior to my brand new event is what my collection window is. Everything else is beyond this still. So I'll only look for events that would now arrive only with event time greater than 12:10. Right. So instead of holding on to your system time as the benchmark for figuring out when to discard events, I'm rather relying on the domain knowledge or the messages that are arriving on the stream itself to figure out when to discard and what to discard. Right. So the watermarks essentially basically give you that. Okay. So in this particular case, I'm basically adding a simple structure, which is words.with watermark. And my words.timestamp is the event timestamp of when the event actually occurred. And in this case, I'm saying my watermark is 10 minutes, right? And everything else basically remains the same thing. Now you're talking about stateful streaming, where now you're holding on to state for a period of time and then collecting events as they come along, right? So the table looks pretty much the same thing. The other two windows are exactly the same. But the last event, the one at 12:05, it was generated at 12:05, but it arrived at 12:11, right? So technically, it's a late event, and because your window length was only 10 minutes and was sliding every 5 minutes, you probably should not have added. If without the watermark, this would have never gotten added into the window of 12:0 to 12:10, because it arrived. Remember, it arrived at 12:11, not at 12:10. Right. So ideally, that window, it should not have been added to this particular thing. But now that we've set a watermark that says even though it arrived at 12:11, my latest event that I've seen is, let's say, 12. Say assume that the current event time for the latest event that I've seen is 12:14. Then I would still let it added, because for me, as far as I'm concerned, it still arrived on time.
Could you describe the scenario again? What would happen if you hadn't set the watermark with that late message arrival?
So if you do not set the watermark at 12:15, even though the event arrived at 12:04, even though the event arrived at 12:11, you would discard it because the event timestamp is 12:04, and that window would have been closed. This particular window object was only valid from 12:00 to 12:10, right? So when you were calculating this window, you would not even have without the watermark, the timestamp would have moved forward, and then you basically would have dropped that event and say, you know what, hey, it's an event that occurred at 12:04, but it arrived at 12:11, which means that I'm not going to process it anymore. But now that you set the watermark as 10 minutes, what I'm saying is, look at the watermark as a look back period, like how further behind I'm going to look back to say, even though the event might have arrived a little late, how long I'm going to still look back and basically add it to my records. That's pretty much what a watermark really is.
I'm also assuming that if you have too large a watermark, you're going to use a lot more memory
Yes.
than maybe you would normally use.
Yes, that's true. Yeah. So longer watermarks, larger watermarks simply means that how much more are you going to carry in memory? How long are you going to wait for events to arrive? And now that is very, very domain specific, and you'll need to figure out what is the right way to do that. But okay, so now we know when we think that the collection basket that we just sent out is full. What do we need to choose? How do we output it, right? So in a complete mode, essentially we materialize every trigger outputs to complete to the tables, so which means that we take the full window of things that have come in, take the full data frame, and then we output all of that stuff to the output source. The output source literally is what we were seeing earlier. So when we say output, all we're saying is this single line, saying what does the dot write stream mean? When you do a dot write stream, you basically give it a path, right? Either you're writing to an S3 bucket or an AWS, an ADLS bucket, or maybe to a Delta table or something. That's all we talk about. What are we going to write once we've figured out, once we've reasoned about all the events that have arrived, once we've collected all that stuff, where are going to put it? In a complete mode, essentially you take the full list of events that have arrived, and then you simply do a flush, and then do an all insert. In the case of an update, you will do something like, I'm going to put only new values, which means that since the time I've started the stream, whatever were the values that have come in, I'm going to do some kind of a distinct between what's already there versus what's not there, and then do an update only, right? In the case of an update, append only materialize after the watermark and lateness have passed. So in the case of stateful queries, you do an append only when the full watermark and the lateness are completed. Then your bucket's full, and then you'll basically do an append operation into your source. Okay. All right. So this is how the typical query looks like. All of this stuff is simply done by these 6 lines of code. With a watermark, group by this operation. So and I didn't show you the first part, which is how do you even create this particular stream. I'll show you in a little bit. But assuming that this is a streaming data frame, you set the watermark, you set the operations that you want to build, right? Do the write stream and the output mode and the trigger, and when you process. Once you have this query, you do a query that start, depending on the platform that you're running on. In Databricks, you don't have to do query start. Start queries actually start immediately the moment you call write stream on them. And then what you see is essentially a streaming query that gets created and then is basically running on the cluster, doing all of these operations for that I just showed you. So again, in terms of the results, there are different type of accumulation modes. What do you want to do when once you've accumulated a bunch of state over there? In the case of discarding, when you say after the Windows specific event time is materialized, the old state is discarded, only the new input, which means that you can basically say after an event time is completed, do you want to still keep the window, or do you want to basically just disregard the window, right? In the case of accumulating, essentially this is the case where you do the group by operations, like how do you want to basically use the windows that you've collected over a period of time to kind of to accumulate to the output data frame. The old state count is added to the new value, and the sum is output. So if you have if you have an accumulating mode as update as accumulating. So in that particular case, your data frame, instead of keeping the full data that's there, is basically going to take the aggregate of the previous window and add it to the new state. That is, your data frame simply just keeps on adding the output of the previous result. So that let's say if you're just counting the number of things that have come over a period of time, your count would just keep on growing as you move these windows and you basically start discarding them. At the end of the discard, all that happens is we take the result that comes out of the aggregate, and then we keep it added as part of the new window, and then we just keep on adding it. Right. So these are the modes that are there. You have a discarding, accumulating, and retracting, and these become super important when there's no concept of a time at all. Where, for example, the Netflix sessionization example that I showed you, right? So in this case, you're going to be accumulating, but you cannot hold on to things infinitely, right? So what you're going to do is you'll basically hold on to some set of events that have come in, and if the user session is still not closed because he's still watching and he's still doing activities, then you do some kind of an aggregate and then put it into an output data frame and then say, and you're going to drop the window. Right. So you've reasoned based on a little bit based on what is done, the number of clicks or number of pauses, the number of forwards, the number of skips, and what is done. And then you basically drop that signal because that's the aggregate that you're really interested in. And then you put it on, you say, at the end of this particular window, here are the metrics I'm going to collect, but I'm still going to keep the stream open because I still haven't received the end of the event. And then you basically keep on aggregating and then collecting it until the end arrives. So that way you're not holding on to the full data, you're at least holding on to the part of the data. So we just walk through in terms of what are these modes. What results are calculated, transformations, when in the event times are those results calculated. This depends on your windowing functions. Processing time refers to is it a stateful stream? Is it how is the state ends? Is it a time-based state ending, or is it an event-based ending of figuring of state? And then what do you do with the results at the end of it? How do you do this? This is the update modes and the accumulation modes we talked about. Right. There's another concept called as a stream joins. Often, you can join a static data frame with a streaming data frame, and you get a streaming data frame, which means that this is often a case where you have some reference data that's sitting in your a reference table, like a lookup table, and you're getting these input sets of data. Like we are getting a bunch of zip codes, and then our zip code has a mapping to state and a district or a county or something. And as the data comes in, you want to look up this table and then and do something else. Very simple example of how these things work, where you can go, your data frame could be a DynamoDB or something like that, and then you're joining that with a Kafka stream that's coming in, and it's a fairly common thing that people do. So again, there's some limitations about what type of joins are allowed, which is the case where you cannot do an outer join, you cannot do some weird type joins, but often typical lookup type stuff are fairly straightforward and easy to do with this. Stream deduplications, same thing. As I said, if you are getting duplicate events, and these are not Kafka duplicate events, these are business duplicate events, where the producer of the event is now delivering with a brand new event ID that that's coming in. You can basically still set to ask you to drop duplicates. Again, remember, without the watermark, with watermark, which basically says how long you're going to wait before you do the dedupe operation on your window. Right. Without the watermark, you basically are saying, as my window moves, dedupe them as things arrive. Whereas with watermark, you're saying, look back for 10 minutes or 15 minutes, and then do the dedupe operations on top of it.
So is that just watching for duplicates inside the window?
Yes.
Then? Okay.
Yeah. Once the data has been materialized into some kind of a table, all bets are off. The data is not there anymore. Then nobody dedupes. So this is a simple API that lets you manage streaming queries. So you start a stream query, and you can basically have all these utility methods that tell you how to handle these. So one thing that happens in the case of streaming queries is they're not easy to manage, because once you start a query, it just goes off and runs. You generally don't have much control. There's no callback mechanisms. Good callback mechanisms as you would get in terms of batch when things fail and whatnot. The best way to kind of handle streaming queries in that case is really to use this API, which is nothing but you get the query object, and you can query the name, the explain. It'll give you statistics about For example, the query.recent progress gives you full statistics about, how many times was the micro batch run, how many results were picked up, what were, if this was something like Kafka, you'd get the offsets that were processed, and how far the query has moved and whatnot, right? So if you're building a monitoring system that is going to rely on, is my query running, is my Kafka topic drained regularly, or am I falling behind in terms of the number of messages that are arriving on the topic versus how fast my stream is running? Essentially these are your API methods to be able to kind of reason that kind of information. Right? Things like back pressure and that sort of stuff. The next part is how do you write to unstreamable things? So remember I said the way query gets structured is spark.read from Kafka, dot transform, do these operations, dot with watermark or with window and whatnot. And then at the end of it, you do a dot write stream, right? Now, what you're saying is eventually when you write to an output location, the output location has to be streamable. Often, let's say you're reading from an input Kafka stream, you're doing all this processing, and then you're writing to another output stream, another output Kafka Kafka topic. That is great because the input source is a Kafka stream, and the output source is also another Kafka topic. Both are streamable source and sinks. If that is the case, then it's never an issue. You can basically simply write to it. But the output of a stream also comes in incremental fashions, if you remember, right? Because ultimately we are doing micro batches. So your output also needs to be a streamable type location. The issue often comes as, if you're going to write to a table like a Parquet table or an S3 bucket, every batch is going to basically give you one Parquet file. Every micro batch at the end of the processing is going to give you one Parquet file. Now, often the problem this results in is, if your micro batch contains, let's say, 100,000 messages, you'll probably process them and write as, let's say, a 100 KB file. Now, all of a sudden, your S3 bucket is full of these small files because your stream is running every minute or every 10 seconds or so, and is putting out these 100K Parquet files all over the time inside your S3 bucket. This results in what is called a small file problem. So not for the input stream, but for anybody who's reading the table via something like Spark, now you're going to have to go read an S3 bucket, which has, let's say, a few million files, small files in there, waiting for you to be read. And reading small files on any kind of cloud data source is a nightmare. You could do that on your HDFS on-prem system, no issues, because HDFS on-prem is super awesome to be able to do file listing. Do the exact same operation on a cloud. You'll take forever to finish the file listing of the process. So, long story short, what it means is, when you write to an output stream, you need to be aware of what this problem is, which is you will end up writing a lot of these small files if you choose an output stream that is not a stream aware, right? Now, you could write to a database, in which case, you're writing these JDBC queries, which is good. Like, databases are great at handling, small chunks of data that are thrown at them, right? So in that case, what you do basically is, you write something called as a for each batch, right? The second method. So on the data frame object, you call this dot for each batch, and inside the for each batch, whatever data was collected as part of the micro batch is now given to you as a data frame object that you can now actually handle as a batch object. So you get a single data frame that contains the entire data that was collected in the window that it ran, and now you're free to do whatever you want to do with it. You could do a batch DB entry and then run it over there. If you're going to post it to a REST endpoint, it's all good. Same thing, you get a batch data frame, open your REST endpoint, HTTP client, and then run it. Or for any other sources, if you write it to Snowflake and whatnot. Along with for each batch, you also have a concept of for each row. For whatever reason, if you want to actually run row by row basis, like every batch data frame that I get, micro batch runs, but I want to process that on a row by row basis, there's also a for each row method. So you can choose whichever way you want to do it. But often, in the Databricks world, we typically go from Kafka to Delta, because Delta is a streamable source. I'll talk about Delta towards the end of it, but Delta is a file format that Databricks has introduced. It's a streamable sink, which means that you can actually write to Delta as these chunks, but Delta is able to handle those small files without actually running into that small file problem. Yeah. All right, so far I just talked about the semantics of just the streams themselves. Any questions before we get into, how do we deploy this? What are the patterns of deployment? What are the headaches that you typically get into when you start productionize these things?
No, I think looking pretty good.
Good.
Plus, we want to make sure I have time for the drawing later too.
I think I have time until 5:45, right, Kevin?
Yeah. We have till 6, but I want to make sure we've got a little time left.
Okay. I think I'll probably need like another 10, 15 minutes, I think.
Oh, okay, that's perfect.
Yeah. All right. So now that we have built a stream, how do you deploy these streams on a cluster? These are, we call the terms that you see, singleplex streaming and multiplex streaming that we talked about. These are Databricks driven terms. These are not industry standard by any means. Everybody has their opinion about how to deploy streams and whatnot. But before we get into it, I'll talk about when you think about deploying streams on a cluster, what are your typical considerations that you should think about, right? And then that should inform your decision about, you go this pattern or that pattern or whatever. Now, a Spark cluster really is, often there is a driver node and there are a bunch of worker nodes, 8, 10, 20, we work with clusters of like 1,000 and 2,000 nodes as well. But always, not always, like always a single driver node. So the first thing that you'll need to think about in a Spark cluster is that the driver is your single point of failure. If you lose the driver, the cluster is gone. Spark is resilient to worker node failures. So if you have a cluster of 10 nodes and one of the nodes fails, it's all good. The data frame and everything is completely reevaluated. Spark, you might see a few failed tasks here and there, but Spark will basically just pick out the processing where it left off and then finish the job without any issues at all. But the moment the driver is gone, there's no more cluster. You have nothing to talk to, right? So in a Spark cluster, your driver is your primary point of failure. Now, in a typical batch ETL workload, the driver does fairly little. What it does really in a batch ETL workload really is it does the query planning. And once it does the query planning, it simply hands off tasks all to the workers to go process them, right? It creates these task objects. The tasks have all the information that they need to be able to process it. All the partitions of the data are all on the worker nodes, nothing on the driver, and the tasks are sent over to get to process these partitions of data, right? And the driver after that is pretty idle. So if you're running a job that runs 45 minutes, the driver's job is done probably in the first 5 minutes, the big job, the first couple of few, seconds, I suppose. It is still there. It is still there trying to collect statistics, accumulate variables, accumulate a bunch of other information, keep a tab on all the workers and the tasks and whatnot. But it's not doing anything active in terms of your workload itself. It's just doing this maintenance type stuff. Whereas when you come to streaming, that fundamental premise is completely different. In the case of streaming, it is your driver that's actually doing the heavy lifting. The driver is the one that goes to talks to Kafka and figures out which offsets have been received, which offsets have been processed, which offsets have not been. It is the one that is allocating your workers to the specific Kafka topic partitions that they're supposed to listen to. And after every partition of Kafka topic gets processed, the worker node simply informs the driver of the set of partition that is processed and where it is moved forward. So the driver actually keeps what is called as a checkpointing location, where it keeps a tab of all of these things as it goes on, right? So in a larger cluster, and if you're running a streaming workload, the driver actually is pretty busy talking to these clusters and getting this offset information and maintaining it, moving the offsets forward, issuing commits back to Kafka, because all of the stuff is primarily happening on the cluster on the driver node. The workers are still doing the processing, but the driver is much more active in a streaming cluster than it is on your regular batch ETL clusters. What that means is, if you're going to decide to run multiple streaming queries on a single cluster, the thing that you're going to be worried more about is the driver failure and not the node failure, right? Much more worried about is the driver failure, I must say, than in the case of the batch ETL workload. So the choice of the driver size, the driver memory, the driver instance type actually becomes super important in the case of streaming workloads. So one thing that we try to do with these patterns is to kind of alleviate that pain, where you're not having to run a single stream that does a lot of work, or basically you spread up the streams into multiple smaller streams, and then and handle it. And then one other piece of information is which type of source, like where your driver pressure is higher, is also dependent on what is your streaming source. If you're streaming off of a file system, that actually is super heavy, simply because somebody has to maintain the full list of files that were there and what has newly arrived and has to do a diff for all of that sort of stuff. If you're streaming off Kafka, then you're just looking at offsets. If you're streaming off Amazon Kinesis, you're still looking for offsets. It's still a lot more memory intensive than, let's say, you're streaming off Kafka. In our experience, Delta, which is another file system that I talked about earlier, performs the best when it comes to having what streaming sources. Basically, your driver memory pressure is the least when we have Delta as your streaming source and not Kafka or Kinesis. Kinesis typically tends to be the worst, and no worse than a file system, of course. But in a singleplex streaming, what we typically say is multiple streams on one single cluster, one per source, event type, and topic. So you have 10 Kafka topics, 10 different things that are arriving. You have 10 different streams all running on the same cluster. Basically, time slicing the driver at that point of time. It's simpler. It's not very complicated. It works great. It's all good, right? If you have streams that don't deal with high volume traffic, that run a few times a day, this pattern works great. You don't have to do additional complexity in terms of how you consume these events, right? All the 10 type of events that you get can be consumed off of on the same cluster. In the case of multiplex streaming, this is where we get issues where you have a lot of different types of events that basically show up on the same topic or often on the same source. Right? Maybe region specific, maybe zip code specific. If you have events coming off of California and if you have events coming off of Wyoming, you probably want to deal them differently because the traffic is going to be different for those settings. Right? So in this case, what we typically do is what we call as a multiplex streaming. We push the delta layer up, wherein we take off the back pressure on the driver having to stream everything off of Kafka topic. We say, we stream everything off of Kafka, put them into delta, which we typically call the bronze layer. So, and then have these substreams that are now streaming off the delta table. Now, the cool thing about delta is like delta can actually be a static data source, like a file format, but delta can also act as a streaming source. So delta is a streaming sink and a streaming source, a batch sink and a batch source. So delta gives you both those options. So in your case, what the code simply looks like, in this case, this particular cluster would do something like spark.read from Kafka from here. And these streams now would do something like spark.read from delta and an underlying partition. So for example, if you have event types A and B, stream them off of here, put them into different partitions between partition A, partition B, partition C, and so on. And then have your individual streams that are streaming off this bronze table, but with that partition predicate, which says, spark.read.format, read stream.format delta, and your path, and then in the query that you say .filter, where partition is equal to type A or partition is equal to type A, and so on. So what this happens in this case is now you have a substream that's running, and this stream is only even interested in events that are coming off of that particular partition and not every partition. Right now, for all you care, all of them could be running on the same cluster, or they could be off of on different clusters. It's a design choice in terms of your volume and whatnot. But there's nothing that says they cannot run on the same cluster. But it's a pattern though where you offload a bunch of work off of your Kafka bucket, of your Kafka topic to Delta, and then have your bronze be, or crudely put, something like a staging layer, and then have from the staging to be more refined onto your other two layers, right? All different patterns basically to productionize streams effectively, because there are definitely some underlying issues with this whole memory issues that typically come with streams. So you're trying to basically figure out what is the most optimal thing that works, rather than saying, here's the perfect architecture that you should always use with streaming. So yeah. So as I said, Dataflow doesn't have a view on one is better versus the other. It's just an architectural pattern that kind of you have to pick and choose what works best for the use case that you have at hand. If you have a lot of streaming that's coming in, it might be okay. If you're making these streaming predictions, right? One of the cases that we often see is you have a machine learning model that's been trained on a bunch of data, and then the model is put into production. You have your Netflix events coming in before the user goes away. You have to tell him what next to watch, and you need a recommendation engine that runs quickly and then produce some recommendations. Like that's a case of where a Singleplex streaming might actually be super appropriate, where everything just comes in. You get a prediction out, and then and there might be streams that need to store the data and reason it and have to learn a lot more analytical models or feed something else. In that case, it might be better off to kind of segregate them separately or have these federated streams, so to say. Okay, I'm close to the end in terms of what I want to talk about. The one thing I do want to introduce is this concept of delta lakes, and maybe if you guys have interest in that time, we probably do something about delta lakes. So one of the biggest issues that you have in the big data world until at least 2 years ago was is this file format issues, right? And then basic things about if you come from a relational background, like these things almost seem trivial that all these big data databases don't even have this thing, which is basic transaction capabilities. Back in the day, okay, in a crude analogy, like a big data literally is nothing but a file system, a bunch of files put together, and people masquerading them as tables, right? And that's all a big data really is. Everything is at the end of the day resolves back down to files as Parquet or CSVs, whatever. Hadoop tried to do it with Hive. Here's Hadoop file system where even though everything is in HDFS and everything is a file, Hive basically gave you a relational field to it. And Spark does something very similar to, it basically reads files but then gives you SQL-like feeling of being able to run it on tables. But at the end of the day, these are files, and files have a lot of these problems. For example, if you run an ETL or a ETL load or any kind of transformation workload, what happens when the workload fails in the middle of it? And then what happens to the data at that point of time? All that happens really is now you have a file that is corrupt. You have a basic set of data that came in yesterday, and then the job ran properly yesterday, so the output was correct. But then today it failed, which means now the output, there's either nothing in the output over there. Often there's not nothing. There's actually something there because there's no all or nothing typing that you typically with a relational database, but you'll get something out of it. So basically, the output location has some Parquet files which definitely are incomplete, and there's no good way to say no. There's no concept of rollback as well, because essentially what you're writing are files and not using a database, so to say. Similarly, as I said, you cannot stream off these files because these are static Parquet files. All they're good at is compressing large volumes of data into very small files, right? So Delta is basically an innovation on top of it, which basically says we still are going to use the open file format that everybody loves in the big data world, which is have Parquet as the primary file format. But on top of it, we'll basically provide these things called as asset transaction capabilities. Now, again, like anybody who comes from relational world and looks at it and says, what the hell is this? Like, this has been there for like 20 years now. But in big data, it's just a brand new innovation because there's no concept of asset transaction capabilities in big data, right? But if you were to write to a Delta table on that, which is Delta table again is nothing but Parquet files plus a JSON log file that maintains the list of these Parquet files. What it does really is, it provides its asset transaction capabilities by basically saying, if your job fails, and essentially if you've not issued a commit at the end of it, there's no explicit commit, there's an implicit commit that happens. That is, the Delta log did not get updated correctly. For any reader that's coming to read this data, I'm going to tell them there's nothing there. Because the way the readers read this data is they have to go interrogate the Delta log, and from the Delta log, they know which files to read. So if your previous workload was incomplete, the Delta log is never finished, or at least is marked as failed, that particular commit point. So when the reader comes and looks for data in that particular location, it says, okay, you got nothing over here. So in a way, that kind of mimics what we call is the asset transaction capabilities, right? That's one of the fundamental innovation with Delta lakes. Along came what we call as time travel, where you can go back to different versions of the data. It also supports things called as merge schema. Merge schema literally is when your data keeps changing regularly. There's no good way, at least the current Parquet world without Delta, there's no good way to handle things like schema type change. Your integer becomes float or decimal or whatever. There's no good way to handle those things. You pretty much have to rewrite your entire data into a brand new Parquet file in the new format. Delta, on the other hand, lets you handle some of those stuff. And then the thing I talked about with small files, Delta handles it by doing something called as optimize, by basically squeezing all these files together into a properly laid out Parquet file format. And Delta is open source. So if you go to io.delta, you'll get the open source version of Delta. The Databricks version of Delta has a bunch more optimizations, primarily around Z ordering and Bloom filters and whatnot. So Z orders essentially rewrites your Parquet file in a way that speeds up your query by basically putting blocks of data that typically gets called together, that gets interrogated together in the same Parquet page blocks. So that way you're not reading a lot of file, and you're not with the file, you're not spending a lot of time parsing the data rather than just going to the blocks of data where it currently exists. So in terms of if you have Databricks as your technology, we typically recommend you use Delta, because you get all the benefits of Parquet, the open format and whatnot, but also some of the other things that you typically don't get with Parquet, with like the Z orders and Bloom filters and partition pruning and a bunch of other good stuff. But it is still an open source utility. A lot of adoption. If you want to look at what other options do you have apart from Delta, Apache Hudi is one of those other projects that's coming up right now. It's still in incubation stage within the Apache ecosystem, but it's getting some traction. Netflix had something called as Netflix Iceberg a while ago. I'm not seeing a lot of development activity around that, but it's another file system that if you want to evaluate what the newer vertical innovation is within the big data streaming world in terms of like what's happening at the file system level and that sort of stuff. Okay, so Delta, Hudi, and Iceberg. Yep, that's pretty much what I had in terms of streaming and how to build real-time streaming applications. Questions?
This has been awesome. It's a great primer to all the streaming on Spark like that.